There are moments in history when a single invention transforms the world in ways no one could have predicted. And then, there are moments when one invention transforms the world in ways no one should have ignored. This is the story of one scientist, Thomas Midgley Jr., whose creations changed modern life, accelerated technological progress, and yet unintentionally caused the deaths of millions of people, reshaped global public health, altered the chemistry of the atmosphere, and even damaged the intelligence of entire generations. And alongside him, another scientist, Claire Patterson, who spent his entire career uncovering the global consequences of those inventions and ultimately helped save humanity from one of the most widespread toxic exposures in history. This is a story about science, industry, human error, and the long-term consequences of short-term thinking. And it begins in the middle of the 20th century, in a world racing toward modernity. 1. A young chemist and a problem much bigger than himself. In 1944, Claire Patterson was a young chemist who had just completed his master's degree. Like many scientists of his era, he was recruited into one of the most secretive military projects in history, the Manhattan Project. His task was technical but essential, separating uranium-235, the rare fissile isotope used in nuclear bombs, from the more common uranium-238. To do this, scientists relied on massive machines called mass spectrometers, devices designed to distinguish atoms by their slight differences in mass. Patterson became an expert at building and operating these machines, but after the war, Patterson returned to academia for his PhD. And his new research project would push mass spectrometry far beyond military use. He set out to answer one of the biggest questions in Earth science. How old is the Earth? In theory, the answer was hidden in radioactive decay. Uranium-238, over a chain of 14 decay steps, transforms into lead-206 at a steady, measurable rate. If you take a mineral that originally contained uranium but no lead, then measure the ratio of uranium to lead today, you can calculate how long that decay has been happening, effectively reading the clock inside the rock. The mineral chosen for this task was zircon. Zircon crystals incorporate uranium when they form, but they reject lead. That meant any lead inside a zircon must have been created by radioactive decay, perfect in theory. But in practice, Patterson ran into a bizarre problem. The lead levels in his zircon samples were far too high, thousands of times higher than they should have been, and inconsistent, completely unpredictable. Something was contaminating every measurement. Something in the water, in the air, on the lab benches, in the dust. This mystery, unwanted lead that appeared everywhere, would come to define the rest of Patterson's life, and solving it would take him to the ends of the earth, literally. 2. A deadly accident that sparked a revolution. Decades earlier, in 1908, a seemingly unrelated tragedy unfolded on a bridge in Detroit. A woman's car stalled on the Belle Isle Bridge. A passing motorist stopped to help. Cars of that era required a manual hand crank to start the engine. As he turned the crank, the engine fired violently. The crank snapped backward, struck his face, and shattered his jaw. Days later, he died. His name was Byron Carter, and he was well connected in the Detroit automobile world. One of his closest friends was Henry Leland, founder of Cadillac. Leland was grief-stricken, and he became determined to eliminate hand cranking from automobiles forever. To do that, he hired a talented young engineer named Charles Kettering. And by 1911, Kettering created a powerful innovation, the electric self-starter. But this new engine had a problem, a loud, destructive problem. High-compression engines were more efficient and powerful, but they suffered from a phenomenon known as engine knocking, where fuel ignites prematurely, creating chaotic pressure waves inside the cylinder. It reduced engine power, damaged pistons, and created an unmistakably harsh metallic sound. If cars were going to become more powerful and reliable, engineers needed a way to prevent knocking. They needed a fuel that could withstand compression without detonating prematurely. And that task fell to a young engineer of extraordinary creativity and, fatefully, extraordinarily little caution, Thomas Midgley Jr. III. The search for the perfect anti-knock additive Midgley tested hundreds of chemicals: camphor, aluminum chloride, ether, melted butter. Most failed. One chemical did help: ethanol. But producing enough ethanol to add to gasoline at scale would have cut deeply into profits. And Midgley was searching for something cheap, powerful, and effective at very low concentrations. Then he found tellurium. It worked brilliantly, but it smelled so foul that the odor seeped into his skin for weeks. His wife made him sleep in the basement for 7 months. Finally, on December 3, 1921, Midgley found what he believed was the perfect solution: tetraethyl lead. It prevented knocking at extremely low concentrations, just 1 part per thousand. It was cheap to manufacture, it was odorless. It made engines more powerful. Midgley called Kettering and said, "Can you imagine how much money we're going to make off this?" 4. A dangerous product with a friendly name. General Motors, Standard Oil, and DuPont formed a new corporation dedicated to producing this additive. But instead of calling it tetraethyl lead, they branded it simply as ethyl, a name designed to sound harmless and conveniently similar to ethyl alcohol. The word lead was deliberately removed from public materials. But inside the new plants that manufactured tetraethyl lead, something alarming happened. Workers began hallucinating, collapsing, convulsing. Within months, dozens were hospitalized. 5 died. Journalists began to ask questions. In response, Midgley held a press conference. In front of reporters, he poured tetraethyl lead on his hands and inhaled its vapors for a full minute. He declared it safe. What he didn't say was that earlier that year, he himself had quietly taken months off to recover from lead poisoning. By the 1950s, millions of cars were burning leaded gasoline, releasing microscopic particles of lead into the air, particles that settled onto soil, into oceans, onto crops, and into the lungs and bones of an entire generation. This was the invisible contamination that had sabotaged Claire Patterson's zircon samples, and that he was now determined to measure directly. 5. The birth of the clean room, and a discovery no one expected. When Patterson moved to Caltech in 1952, he built a new laboratory from scratch, but instead of designing for convenience, he designed for purity. He removed electrical cables from the walls to replace lead solder. He washed every surface with chemical cleaners. He created positive airflow so dust couldn't drift inside. He required full protective suits for anyone entering. Without realizing it, Patterson had invented something foundational to modern science and technology: the clean room. Inside this meticulously controlled environment, his measurements finally worked. And through them, he reached a groundbreaking conclusion: meteorites, remnants of early solar system formation, were all about 4.5 billion years old. This became the modern age of the Earth. But Patterson wasn't done with lead. Now that he had a lab clean enough for precise measurements, he turned his attention toward the environment. What he discovered changed public health policy worldwide. 6. Lead in the oceans, lead in the ice, lead in our bones. Patterson began analyzing ocean water. If lead was naturally occurring, its concentration should be the same at every depth. But it wasn't. Near the surface, lead was 10 times more concentrated than deep water. Then he traveled to Greenland and Antarctica. Ice cores revealed the history of atmospheric lead over thousands of years. Levels spiked dramatically in the 20th century, exactly matching the rise of leaded gasoline. Finally, Patterson compared lead levels in bones and teeth of modern Americans with those from Egyptian and Peruvian mummies. He expected a moderate difference, maybe a factor of 10 or 100. The real number was closer to 100. Modern Americans had 1,000 times more lead in their bones than ancient humans. 7. The toll: intelligence, crime, and millions of lives. Lead is a neurotoxin. It mimics calcium, embeds itself in bones, and disrupts the brain's ability to transmit signals. It damages the developing nervous systems of children most severely. Even tiny exposures worsen learning ability, attention, memory, impulse control. Studies of baby teeth later showed that even low lead levels, far below what was once considered safe, correlated with decreased IQ and increased behavioral problems. One staggering estimate from 2022 found that more than 170 million Americans exposed to lead as children collectively lost over 800 million IQ points. Some researchers have found an eerie trend. The rise and fall of violent crime in the late 20th century tracks closely with lead exposure levels 2 decades earlier. While crime is complex and driven by many factors, the correlation appears globally in the US, Canada, Britain, and Australia. The estimated death toll is even more sobering. A 2018 study found that lead contributes to roughly 250,000 US deaths per year, mainly from cardiovascular disease. Over the past century, that implies around 25 million American deaths, and possibly 100 million worldwide. Most of this damage traces directly back to Midgley's decision to put lead in gasoline. 8. Another invention. Another global crisis. You might hope that after seeing the chaos caused by tetraethyl lead, Midgley's career would have changed direction. It did, but not in the way we might wish. By the late 1920s, GM was expanding into household appliances. Refrigerators used gases that were either toxic or dangerously flammable. Midgley was tasked with finding a safer alternative. In 1928, he created dichlorodifluoromethane, a chlorofluorocarbon, later known as Freon. During its debut at the American Chemical Society, Midgley inhaled a lungful of the gas and blew out a candle to demonstrate its supposed safety. Freon was non-flammable, non-toxic, stable, and effective. It revolutionized refrigeration, air conditioning, and aerosol sprays, but it had a devastating atmospheric effect. CFCs drifted into the stratosphere, where UV radiation broke them apart, releasing chlorine atoms. A single chlorine atom can destroy thousands of ozone molecules, and by the 1970s and 80s, scientists discovered a massive seasonal thinning of the ozone layer over Antarctica. More UV light meant higher skin cancer rates, more cataracts, and damage to plants and plankton. CFCs also turned out to be extraordinarily potent greenhouse gases. The historian J.R. McNeill wrote that Thomas Midgley had a greater impact on the atmosphere than any other single organism in Earth's history. 9. A tragic ending for a man who reshaped the world. In 1940, Midgley contracted polio, which left him severely disabled. Ever inventive, he designed an elaborate system of ropes and pulleys to help lift himself out of bed. On November 2, 1944, he became entangled in the system and died of strangulation. Killed not by his chemicals, but by one last invention. 10. Patterson's fight and the world's slow awakening. While Midgley's inventions spread around the globe, Claire Patterson was fighting to reveal their consequences. He spent decades confronting industrial lobbies, government agencies, and scientists funded by corporate interests. But evidence accumulated. The Clean Air Act took shape. Countries began banning leaded gasoline. Japan was the first in 1986. The United States followed. By 2021, Algeria became the last nation to phase it out. The United Nations estimates that eliminating leaded fuel now saves more than 1 million lives per year. Even today, lead exposure remains a major global health problem, much of it from batteries, industrial waste, and aviation fuel. But without Patterson's work, the world would have continued unknowingly poisoning itself for decades longer. Patterson once quoted Benjamin Franklin, who warned in 1786 about lead's dangers. "You will observe with concern how long a useful truth may be known before it is generally received and practiced on." Franklin couldn't have imagined how prophetic his words would become. 11. The legacy of 2 men. Thomas Midgley Jr. did not set out to harm the world. In his lifetime, he was celebrated as a brilliant engineer and chemist. His inventions solved real problems and propelled industries forward. But they did so with catastrophic long-term consequences. Claire Patterson, in contrast, spent decades trying to undo the damage, often alone, often ridiculed, often ignored. Midgley's legacy is a warning. Technological progress without caution can be as dangerous as ignorance. Patterson's legacy is a reminder. Science, when pursued with rigor and honesty, can protect humanity, even from its own mistakes. And together, their stories show how profoundly one person can alter the course of global history, intentionally or otherwise.